Hello, and welcome to the seventh lecture in the Jabrah reinforcement learning series. And this lecture, we're actually going to go through the policy iteration algorithm, how to actually implement it for this environment. So we're actually going to go through real code where you actually solve some version of the problem where this guy learns to move and reach the state where you've got KFC. So if you don't remember the problem description, please check the previous lectures. Um, Even the first lecture has the full description of the problem towards the end of it. So I will also provide the code for what we're going to do here, and you can find it in the Jabrah tutorials GitHub repository. I have put the link in the description below, so please check that out, and you can actually go through it, understand it, play with it, see what's happening, and I will actually leave you with some exercises that you can actually try to extend how this algorithm works, basically. So with that said, I will start uh, by saying that if you remember, you are this agent in a state and you're just trying to navigate to reach the point where you have KFC. So I will straight up start with some definition, like the reward when you're in the KFC state, we're gonna say this is plus 10, and the reward when you're at the state where you've got a stick, this should be minus 10, so that's bad, you don't want to be there. And the reward for being in a sort of like a blank tile state is minus 1. So that's just referring to everything else here. The reward is minus 1. So it's probably in the agent's best interest to actually navigate through this as quickly as possible, because every single time step you're losing -1. That's pretty much what this is saying. So we are going to solve a simple version of this problem where we're going to assume the following things. First of all, we'll say that, okay, the agent is in a state, so probability of reaching the next intended state, right? So S prime given S comma A, this is the transition probability, right? So if you remember, we did say that coming from a state, you have like numerous options, like you might end up in the state or you might end up in the state depending on the action you choose to take. But if you know that you took the right action, this is going to happen with the probability of, let's say, 1 in that case. So once that action is chosen, you will go to the next state with a probability of 1. So this is kind of like very vague, so let me actually clarify what I mean by this. But let's say that probability that you end up in, if we call this state 0 and this state 1, so the probability that you end up in 1, given that you're in 0 and you take action right, this is equals to 1. So we're assuming that you have a perfect controller and you'll end up in this state if you take the action right. That's basically what I'm trying to say here. So if the probability of ending up, if this is 2, given that you're in 0 and you take the action down, the probability will be 1. So what that means is the probability of ending up in, let's say, state 2, the state here, given that you're in state 0, right, and you take the action right, you should know what this is, right? This should be 0, right? That's the idea. Because you are in this state, obviously, if you take the action right, you'll end up here and not there, and so forth. So we're just solving a very simple version of the way you have a perfect controller. You will understand soon enough what that means when we go through some examples where you might not have a perfect controller. I'll briefly touch on that at the end, maybe leave it as an exercise for you. But the idea here is that if you move to a certain direction, it will happen with 100% probability. That's the idea. So hopefully, like with the code, it will make it clearer and all. Right. So let's go to the code. So I've taken the liberty of actually creating the environment for you. So the focus of this lecture is on going through the algorithm, the policy iteration algorithm, not the creation of the environment and such. So if you really want to understand that kind of stuff, like how I went through creating this environment, you can go through the code. Like I said, you should find it in the description, in the link to the repository where I put this code, basically. So given this, now we have an agent, and the agent is a position, right? You can get position, you can set position. So this should be like pretty clear that you have an agent there. And then you have an environment, and in this environment you can set the grid size, and if you look carefully through here, we have a 5 by 5 grid, right? So that's the same environment that I am creating here, a 5 by 5 grid environment and so forth. And then we come down to the game widgets, right? So we have different type of cells. We have a blank cell, right, where there's no reward. We have a whooping cell where you get caught and get a beating, and the reward there is -10, and the KFC cell, if you win, where you get +10, right? So each cell state is associated with a couple of things. So in each cell state, if you remember, the environment is like what kind of information does each cell hold? This is what the cell state is in this scenario, right? So what kind of information does each cell hold? Well, the position, where is the cell? Is it position 0, 0? Is it position 0, 1, and so forth? The reward that that cell will give you, depending on the type of cell it is. If it's a whooping cell, you know you get a -10 reward. If it's a KFC cell, you know that it's a +10 reward, and so forth. And then we have the cell type, which is described here, and whether the cell is a terminal state. So what is a terminal state? In this case, a terminal state, we describe that as the following. All these states here, if you get caught, right, the game is over. You got caught, you lose the money that you had, and you get your -10 reward, and it's done. You can't go anywhere else from this state. That's what we're calling the terminal state, right? So this is a terminal state because you got caught, and there's no movements you can make from here. The same goes for down here. This is also a terminal state, right? Because once you reach the KFC, then the whole scenario is over. So this is also a terminal state, and this also counts, all of these circled ones are our terminal states. This is basically what we're referring to here. And with that said, so we have information about whether the cell is terminal or not, and this is the children. Actually, I don't think I need this. This was probably when I was trying to focus the possible things that we may need, but for now, just ignore this. So, and the next thing is just, okay, this is the same stuff: position, reward, cell type, and its terminal. You can go through the code and see what it is. And finally, this is basically the logic. So I am using Pygame for this. So you can actually install Pygame. You can just go to you can Google Pygame, and you can go to their repository, and you'll get the steps of how to install it. I'm not going to go through that either. It's pretty simple. And with that said, so I'm just going to quickly go through. We have a class for the game here, where you set up the controller. So the controller is basically a bunch of keys, whereby if you press left, it will move left. If you press right, it will move right, and so forth, right? That's basically what the controller is. And you can set the environment, the agent, the policy. I'll explain this stuff. And this is for drawing the environment. I'm not going to go through this. This isn't important for this lecture. And also all of this is not that important. The only thing you need to know is that if we have a policy, if we feed this class with a policy, it will use that policy, right? And if we don't, it will just use the controller being the keys on your keyboard, right? So if I run this application right now, because we don't have a policy yet, we did not implement the policy iteration algorithm, it will use our controller. So let me run it, and let's see. This is the wrong Jabrah tutorials. Okay. So yes. So we don't have the policy yet. Okay, so sorry about that. I need to fix a couple of things, because here I'm supposed to implement the policy iteration algorithm with you guys, but I imported it here. So let us comment this for now. Right. Okay. And let's reset everything and start from the sorry, that's the wrong one. Let us reset, and okay. So this is what we get, right? So right now I'm controlling this with my keys, right? On moving right, I control this, and if I want to move down, I can control that as well, right? So basically it's just my key movements that are determining like where I end up moving. That's the basic idea here. So with that said, as you can see right now, if I click, it's quite slow, and the reason for that is actually a variable here in the config. So here you can actually set a couple of parameters such as screen size, cell height, cell width, velocity, and so forth. This is actually to do with Pygame, and you will need to read through the code to actually understand what's happening. But if I reduce the delay, then I think I should be like able to move faster, as you can see, much better. Right, so that's the idea. You're just trying to find a way for you to navigate. Oh, I reach KFC, I win, and stuff like that. So that's the idea here. This is the problem we're trying to solve, right? But we don't want to be using the controller. We want to actually write our own policy iteration algorithm so that we can actually solve for this problem. So as you can see, like trying to create a class here. So first, let's actually start the coding. We're gonna import random. I'm gonna need that later for randomly choosing the actions. You need to start with the random policy. But let's start with our class policy iteration, right? So this is our initial class. Now, starting with this class, we need to define an initializer for this class. So what are we going to initialize this class with? We're going to initialize it with, okay, you always need a cell, okay, and we're going to also put cell states, right? So this is how we start, and first of all we need to actually define a couple of things, like so we're going to say 0. We need to map like some numbers to the action we'll take, right? So 0 we can say is move up, 1 is move right, 2 is move down, and 3 is move up. So that's basically what we'll do here. And next we need to define like an epsilon, like a convergence parameter, but I'm not gonna actually do this right now, so that actually let me just define it anyway. So after epsilon just goes to 3, you don't have to worry about this now. I'll explain what that is later. And next we need to actually define what our actions are, right? So after actions is equals to 0, 1, 2, and 3. So these are our actions essentially. And what else do we need? So since we're starting this policy iteration algorithm, if you remember, please look at the pseudocode as well as we're doing this. This will actually be helpful for you to understand how things are correlating with each other. So the first thing we need is a state dictionary, we need a policy dictionary, we need a value dictionary. So I'm just gonna create another method here that I will call create let's say state policy dict, right? And this will take so there's self, and we need the self states, right? So that's the basic idea. So if you remember what the self states are, these are the states that have all this information, right? Please remember what a self state is, and each object of it should have all this information. So this is gonna be important. So this is pretty much what you really need to know what it is. So the game widgets, just please go through this file, because it's quite important. And with that said, so we need a state dictionary, like I said, and we initialize it to, okay, and we need a policy dictionary. Policy dictionary, that's basically telling us, like, in this state, what are we supposed to do. And finally, we need a value dictionary, which tells us the value of being in a particular state, right? That's what the value dictionary is. So basically, we need to initialize this. So for cell state, in cell states, what do we want to do? Like, first of all, we want to initialize the state dict, right? And say that the cell state dot position, right? So the position will always be our key here, right? Is equals to cell state. We're going to need this later. The reason why we're keeping this as the key and the value is the actual object itself, because later on we're actually going to need to access some parameters of the object, like the reward or the whether it's terminal or not. So this is going to be important. So with that said, we have our cell state, and the next thing we need is the policy dict. Again, what is our policy for the particular state? So in this position, if you remember what pos is referring to, I'm just going to show it again. Position is where we are. This is actually, we can mark this as follows. This is actually 0, 0. This will be something like 0, 1. This will be something like 1, 0. So it's basically like a grid and so forth, right? That's the idea here. That's how we mark our grid. So with that said, I am gonna go back to the code, and we are going to say that this is equal to, we're gonna say random.choice, right? We're gonna choose, initially we don't know what our action is, so we'll choose randomly from solve.actions, right? So that we can have a random action. That's the idea. And so how about the value dictionary? Well, the value dictionary will initialize all the values to 0, except for where we have a terminal state. This is where we differ a bit from the pseudocode that you saw before, because the idea here is that terminal states, the value is never going to change, right? If you reach a terminal state, for instance, where you have KFC, you will always get plus 10. If you reach a state where you have the whooping stick, you will always get negative 10. So those terminal states will never change. That's the idea, right? So basically we need to write an if condition. So if cell state dot is terminal, right? That's what we want to check for. If cell state dot is terminal, what are we gonna do? We're gonna take the value dict, right? Then it's cell state dot position, right? So wait, yes, that's right. And if it's a terminal state, we'll just give it its reward value, right? So state dot reward. So that's the idea here. Else, so in any other condition, we are gonna initialize the value grid of cell state dot position, and we're gonna set this to 0. That's the idea. So as such, we'll return our state dict, our policy dict, and our value dictionary. So with that, we can say self.state dictionary, comma self.policy dictionary, comma self.value dictionary is equals to, so we're gonna say this is equals to self.create state policy dictionary from the cell states. right? So for now, let's just print the value dictionary to make sure that everything is working as intended, right? So I'm gonna just print this and try to run this from here. So now we can import this, and we can actually say policy iteration algo is equals to the policy iteration, and we're supposed to give as input the source states. These are the states that are here. So this is where I'm initializing this algorithm, and yeah, I guess this should be fine. So let me try running this. Cannot import name policy iteration. Oh right, my bad, I misspelled it here. Policy iteration. And okay, so this is what we have, and we have -10 at 4.1, -10, and at 4.4 we should have +10, which means that things should have been initialized properly without any problem. Okay, so with that said, that we've completed the initialization process, which was basically phase 1, right? So the next thing we need to do is like get future states, right? So someone so get future state. So basically the idea is that someone gives us a current state, right? Current state, and what we're supposed to do, and let's say an action, and from this what we want to do is basically like see that what is the next state we'll be in if we're in a given state and we take a particular action, right? So that's what getting future state is. So for that, actually I think I have some conditions here that we can use. This was for creating the grid, but I think I can apply this here as well. So this should be fine. No. So instead of this, we're gonna say, so if action equal to 1, so initially we're gonna say that the new position is equals to the current, I should call this current position, not current state. So current position. So if action is equals to 1, then the new position is equals to this. I might have to cheat here and just add an environment site here. This is probably a oh yeah. So let me just change there and there. Oh, that shrunk very, very quickly. So let's see, what did I do here? So it seems like, let's see if I can increase the size of this, because suddenly it became too small. So where was I? Okay, so this is not working. Let's see, view. Zoom in. Okay. I don't know if you want me to control plus equals. Okay, maybe this is too much. Okay, so this should be fine. Okay, so this is where we were, and given this, I just set the environment size variable here. So basically what this is doing is that we are in a given position and we're just trying to find out what our new position is going to be. Again, this is not so important for this understanding the algorithm itself, but if you just want to go through, so this should be, so if action is 1, this will be what our new position would be. Try to convince yourself why that is. If action is 3, this should be the new position. If action is 2, this should be the new position, and if action is 0. So you see these min and max operators, that's so that we don't go beyond the actual grid size, right? Because if you reach the grid size 5, then the agent will be out of the screen. We don't want that. So is that fine? Yes, that looks okay. And we're gonna return the new position. That's the idea here. So let me just look at this again. Yes, it looks about fine. So the next thing we need to define is QValue. So right now I'm just defining functions that will help us when we actually go through the whole implementation of the algorithm. So if you remember from QValues, like you're computing QValues for state action pairs, so that is the value of being in a particular state after taking a particular action, right? So first of all, if I take an action, I'll end up in a new state, and this state is what? Self.getFutureState, right? That's why we have that. And our current position is our current state, and our action is the action we took, right? So this is our future state, and the Q value is actually equal to self.stateDict, right? And that's the future state, right? Dot reward. So the reward of being in this future state, right? Plus self.valueDict, right? For the value of the actual state that we're in, right? So that's why we need this valueDict and stuff. And finally, we're supposed to return Q. That's how we compute the Q value. And finally, now we're gonna go through the policy evaluation algorithm. So make sure you have the pseudocode next to you in case you've forgotten how it works. But if you remember, then this should be quite simple for you. So you've got self. Actually, we don't need any parameters here. So I'll just print out policy evaluation, right? So we'll have our while true, right? We're gonna start with a delta of value 0, if you remember. So for state in self.stateDict, what do we want to do for each state? First, we want to compute v, right? So I have the pseudocode next to me right now, so make sure that you also have that. It will help guide you basically on how to actually implement this. So this is basically the self.valueDict, right? So for the particular state, if you remember. So that's the value of the state we're in right now, right? So first we should probably check, because let's see, this is the value of state. So in case the state is actually a terminal state, right? So if self.stateDict state, right, dot is terminal, we want to skip that. We don't want to update its values or anything, right? We don't want to update terminal state. So next state, S prime computation here. That's what we want to do. I'll compute the S prime, and we're gonna say self.valueDict state, right, is equal to self.QValue, right? And what's the Q value for? We're gonna put here the actual state, and what's the action? The action is the action under the current policy, so we need the policy dictionary for that, right? So the policy under the current policy is the one that determines the action we'll take here. So after that, we update delta. As you can see from the pseudocode, it actually becomes the maximum between the current delta and the absolute value between v minus this should be v minus self dot value dict for the current state. That's the idea here. So, and we need to set if delta is less than self dot epsilon. Now you know why we had that epsilon. In the pseudocode, this is represented by theta. Just epsilon may make more sense in this case. So we break, and we have evaluated our policy. And if we evaluate our policy, next we need to improve on it, right? So that's policy improvement, right? Again, we need a self here. So print policy improvement. So while true, actually not this, I think we should first set policy to stable. Policy stable is equals to true, right? And then we're gonna check, like for each state, if the policy has changed, and that will be by comparing it by the maximum overall, actually the agmax, overall Q values and so forth. So for state in self.stateDict, right, what are we gonna do here? The old action, right, according to the pseudocode, is self.policyDict state. That's what our old action is, and we need the value of this old action. And the reason for this is the pseudocode, if you saw, it only checks if the action changed, but sometimes we can have two actions with the same value. So we want our algorithm to converge, and we want to avoid that scenario. So if two actions have the same value, then comparing the actions alone is not going to be enough to see if the action has actually changed. We need to actually compare the value to see if the value is increased or not. This will only make sense if you actually have the pseudocode with you right now. But in any case, old action value, this should be equal to self dot, what word did you define here? Q value, right? Yes, we can use the Q value for the state, and the old action, right? That's the value of this. And we can define what's the best action in the beginning. We can say the best action is equals to the old action, and the best action value is equals to the old action value. Okay, so my approach here, I'm just going to iterate through all the actions and see if any action is going to give us a higher value, and if that be the case, that was going to be our new best action. And if we have a new best action, it means that the policy is not yet stable, which means we should go back to policy evaluation and so forth, and we keep going back and forth until the policy is stable. Now this approach is just to help you understand how the algorithm is working. Programmatically speaking, it's not the best way to implement this. We can actually vectorize this code a lot and make it much faster, but that's not the goal here. The goal is to learn. So for action in self.actions, what do we want to do for each action? Of course, the first thing we want to do is compute the action value, right? And we all know what that is. That's the self.q value, right? So the q value between so the state and action as usual, current state and current action. We'll get the action value like that. So if the action value is greater than the old action value, right? It's like, oh wow, it's greater. So what are we going to do now? We're going to set the best action to be the current action, right? And the best action value to be the current action value. Right? That's what we need to do. And of course the policy is no longer stable in this case. So we can set the policy stable variable to false. That's the idea here. And finally, we need to set change the policy. So for policy dict state, the new policy is the best action, right? That's the idea here. And finally, we're gonna return whether the policy is stable or not, right? So finally, I'll define the run function for this algorithm. So this is again, I can say policy stable is equals to false. I'm just doing a rushed implementation here, so please forgive the lack of how would I call it, beauty in the code of some sort, I guess. So but I'm just hoping that it's clear to you like what's happening here. So while true, what are we gonna do? So while true, self dot policy improvement, right? And then policy stable is equals to, so I actually don't need to define this right now. So policy stable is equals to self dot policy. So this shouldn't be improvement, this should be evaluation first. That's my bad. So self dot policy evaluation, then policy improvement. Then if policy is stable, what are we gonna do? We're going to break, right? That's basically how we run our algorithm. So for you to actually put this algorithm here, I'm going to say that's the policy iteration algo.run. I need to run this algorithm, and this is what's supposed to give me my policy, right? And here before I had policy run, which was making it use the controllers, but now I have a policy, and that should be fine. And probably I should change this config to be slower so that we can actually see what's happening. So that pretty much completes this algorithm. So let's see if it runs or if I've made some mistakes. Oh, there you go. So, and it has paused for some reason. I wonder why that is. Okay, so you are not moving. Let's see what happened. Run the game part. The draw dot environment dot run. Okay, let me reduce the delay and see if that's the problem. Sorry. Okay. Oh, sorry, I have to do a bit of debugging here to find out what's wrong. So after this, are we terminating? So I'm just gonna print here to make sure that no, that's not the problem here. So let's see, what else did I leave behind? It's almost like it's not being redrawn rather. Okay, policy iteration algo run from the source state here. That's fine. So what happened? Return. I see. That's the problem. So after here, if policy stable, we're supposed to return self dot policy dictionary, right? We need to return the policy. That was the problem. So with that said, we can now run it one more time. Oh, sorry about that. And there you go. That was really fast. So let's try to slow it down so that you can see how it's moving. So I'm gonna slow it down a bit, and let's see once again. So you started the state, move down, right, and so forth. That's the basic idea. Okay. So this was a simple version of the problem, which is why this happened. But what you need to also understand is that if you look at the pseudocode, we're also dealing with the probability distribution over the action space and the future states, right? Because we might take an action and it might lead us to different states with different probabilities. So in that case, we would have a defective controller, for instance, that if you say move right, it will move maybe right with an 80% probability, and with a 20% probability, maybe the controller might move in any other direction. So once we add this kind of randomness into the environment, then what would change here is how we're actually computing our Q values and such, because state is not just gonna be just a great future state. We'll be reaching this state with some probability and other states with a different probability. So we would actually need to go through a probability distribution. So as an exercise, try to think of that scenario. Like imagine the controller moved in its intended direction with an 80% probability, and with a 20% probability it moved in any of the other three directions. How would your code change, right? That's the thing. For one, what I can tell you for sure is that if you look at the current movement, let me run the code again. It's moving so close, yes, to the sticks because it knows that it has a perfect controller, right? But the thing is that if you were to add this extra randomness, what's gonna happen now is that, okay, it's not gonna be moving around this area. It's actually preferable to move through here so that it can avoid the sticks as much as possible, because with some probability it might end up there, right? So for you to actually understand that, you can try modifying this code or implementing your own if you want, and adding this extra randomness. If there's a real demand for it, I might create a future video on that. Here I just wanted to show a simple demonstration of how the policy iteration algorithm works. And from this simple demonstration, you should get an intuition of how you can actually improve it, maybe vectorize it, or how to add this kind of randomness, not only through the future state space, but maybe the action space, maybe the action space also follows the probability distribution based on the state that you're in, and so forth. So adding this kind of like randomness into your environment, it will actually make you get closer to actual problems that you're solving. But for the sake of trying to move forward, I will actually stop here with this lecture. I'm not gonna go through right now this extra randomness probability distribution over the state space or the action space and such matters. Actually extending this is quite trivial. You just need to just think a little bit, like it's not that difficult. And I'm actually gonna go prepare for the next topic that we'll be going through, which will be on probably value iteration, and maybe after that we're going to look at Monte Carlo methods. But for now, this is where I end this lecture. Thank you very much.